Recording. Alright, so number of things to do today. So I am planning on going over questions 7 and 8 from the homework, okay, because those are definitely extra confusing. I want to talk more about multiplexers, demultiplexers, decoders. I want to talk about the 74LS47. I want to talk about Lab 4 and about adders. But before we get into that, any questions, anything that somebody wants to know about up front? Do you know when this class period will be uploaded to YouTube? I have to leave at 1. I'll start the upload probably about 3 o'clock. So it should be up by like 4 or 5. I have a slow internet at home, but Clark's internet is funny. Their download speed is kind of low, but their upload speed is blazingly fast. So I can make a 3 gig video and upload it in a few minutes from campus, which is awesome. From home, I've got really pokey upload speed, so. All right, well let's jump into some of the stranger homework questions. So probably the strangest is question 7 followed by question 8. So question 7 needs us to use a demultiplexer, a demux, and I told you for these, it's okay to refer to the solved versions. So let's talk about a demux first of all. So a 3 to 8 demux looks something like this. So let me use the same symbols they use, ABC. It's usually, like input 2, input 1, input 0, something like that. And it has 8 outputs, which we'll just call outputs, or let's just call it Y0 through Y7. Alright, so it's a big circuit. So here's a way to think about what a demux does. Let's say exactly one output is asserted. Based on the inputs C, B, and A. And I'll tell you what I mean by asserted in a minute. But based on these 3 inputs, exactly one output is asserted. And the output that's asserted is simply what the numeric value of the inputs are. So here the inputs are all 0. Output Y0 is going to be asserted. Here the inputs are 0, 0, 1. Y1 is going to be asserted. 1, 0, 0, that's the number 4, Y4 will be asserted. 1, 1, 1, that's the number 7, Y7 will be asserted. Okay, so what do we mean by asserted? Now normally when we talk about turning on an output, we think of putting a logic 1 on it, right? When you turn on a light, you think of running current through the light and the bulb comes on and you see something, okay? So when we say asserted, though, it can mean different things. So in question 7S, you notice this little circle up here. Remember these circles, we call them bubbles. They're basically inverters. And these lines, which are normally, min-term 0 through min-term 7, they have the little complement symbol after them. This is actually M0 naught. This is M7 naught. So for this setup, where you have these circles on the outputs, asserted means set the output to 0. So in this circuit, right, all of these outputs would be 1 except the one that's asserted. This would be all 1s but a 0 over here. The second row would be all 1s except a 0 in that Y1 column. The last entry will be a 0 in column 7 and then a 1 everywhere else. Okay, this is very common, and when you're working with devices, you have to look at the data sheet, and sometimes you'll see a description of a DeMux, and it'll have these bubbles on the outputs. That means they're what we call active low, okay, or asserted low. So that's outputting zeros on one of these lines, whichever one was selected here. So this is a fairly useful circuit, right? If we look at just the output F2, depending on your values of your inputs, all of these outputs are going to be logic 1, except for one of them. Okay? Now, if you happen to have an input value 0, 0, 1, line 1 is going to be the line that has a logic level 0. And if line 1 outputs a 0, that 0 comes down this wire, it goes through this inverter, and now you have a 1 going into your OR gate, and your output will be 1. On the other hand, if your input combination is 1, 0, 0, then output 4 will be asserted, which means it will be low, logic 0, which comes through this wire, gets inverted to a 1 goes into the OR gate, and again F2 is equal to 1. And the last case, if your inputs are all 1, you have a 0 on line 7, gets inverted to a 1, your OR gate outputs a 1. So F2 will be true, it'll output a 1, when you're asserting either lines 1, 4, or 7. Okay, and if you look at what that means in terms of the input combinations, it means those input combinations correspond to minterm 1, minterm 4, or minterm 7. So in this case, F2 is just the sum of M1, M4, and M7. Okay, which is what we have down here. And this is done by inspection. You don't have to actually do any computations, K-maps, things like that. It's an analysis of this. F1 looks the same, except it uses M3 and M6, okay, but it's complementing the output. There's another inverter. So F1 complemented is the sum of minterms 3 and 6. Well, if you want to complement a function written in compact form, simply write the compact form that uses the other values that you didn't list. Right? And think about it, if you have a truth table with 1s and 0s, to write the sum of products in compact form, we write down each of the minterms where the output is 1. Well, if we want the complement of that function, the 1s become 0s, the 0s become 1s. So we're going to write down all the minterms where the output function was originally 0. Okay, which is exactly the ones where it was not 1. So if the complemented function is the sum of minterms 3 and 6, the complement of that is the sum of minterms 0, 1, 2, 4, 5, 7. Okay, so that's what's happening in 7S. And like I say, that's a fairly reasonable circuit, right? It's writing these things as sums of products. 7U is arguably not very useful, okay? But it's a good exercise to analyze. So here, you know, the outputs are not complemented. So our DeMux in 7U just looks like this. And so on. And so we can write each of these outputs as a sum of products, or, you know, as a product term. Y0 is only going to have a single 1 output, right? All of these are 0. Y0 is asserted only in this row, which is C bar, B bar, A bar, which, you know, just happens to be minterm 0. And Y1 is going to be 0 everywhere except this second row, which is what? C bar, B bar, A, which just happens to be minterm 1. And Y7 has a single 1 output, which is in this bottom row, which happens to be CBA, which is minterm 7. And so the equation for each of these 8 outputs, Y sub I, is just minterm I, which is why we have these minterms written over here next to these output lines. Okay, so with that idea in mind, we can look at F2, for example, and we can say F2 is going to be 1 when? Well, it's going to be 1 if if any of the inputs are 1, okay? Well, this first line gets inverted, so anytime that this output is 0, F2 will be 1. Anytime that this output 4 is a 1, F2 will be 1. And anytime output 7 is a 0, that'll get inverted, F2 will be a 1. So F2 is 1 when any of the following three things happen. Y1 equals 0, or Y4 equals 1, or Y7 equals 0. Okay, so I've just transcribed that. Y1 is 0, Y4 is 1, or Y7 is 0. Well, let's look at Y1. Y1 is 0 almost all the time, right? Here, 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 all of these, Y1 is 0. The only time Y1 is non-zero is in this second row. And in that second row, Y4 is not 1, but Y7 is a 0. So in every single row of this truth table, at least one of these conditions is true, which means F2 is equal to 1. So what's your equation for F2? It's just 1. It's always a 1. Okay, which is why I say this is not necessarily as useful a circuit as the previous one. Because it doesn't matter what you put in for A, B, and C, this is always going to be a 1. That's quirky, but that's what the circuit says, right? So do the same kind of analysis for F1 and F0, and you'll probably get similarly kind of goofy seeming results. But think through it, right? Just think about the inputs, what the outputs are doing, and how these OR gates respond to that. All right, question 8. So we have a circuit with a multiplexer inside. Let me go ahead and print this. We have a circuit with a multiplexer inside. We're told what the multiplexer does. Okay, we've got the description of that. So the output takes one of these inputs and sends it to F. And this is related to something we call compressing a truth table. Okay, this is actually decompressing. So let's write this function f as a function of a, b, a1, and a0. Okay, so let's do a, b, a1, a0, and let's write f. Okay, so first of all, right, this input D0 is just A0. This input D1 is just A1. D2 is ground. Okay, so this is always a 0. And D3 goes to 5 volts through a resistor, so this is always a 1. All right, and S1, S0, those are just A and B. So let's look at the first 4 rows of this truth table. In each of these rows, the value of A is 0. The value of B is 0. So in each of these first 4 rows, A and B are 0. We know what F is. F is whatever D0 is. Okay? And regardless of where we are in this truth table, each group of 4, A and B, always have the same value, right? So let me make a more simplified truth table. that just looks at the values of A and B. Okay, if A and B are both 0, then F is whatever the value of D0 is, which is just A0. If A and B are 0, 1, then F is the value of D1, which is A1. If A and B are 1, 0, F is D2, which we already analyzed is a 0. And if A and B are both 1, F is D3, which we said is a logic 1. So here is something like a truth table for F as a function of A and B. And it's not exactly a truth table because we don't just have zeros, ones, or don't cares. We have these other things, A0 and A1, in the outputs. But logically, this describes how your circuit behaves. Okay? In some cases, F is just equal to the value of A0. In some cases, it's equal to A1. In some cases, it's 0 or 1. So if we have this, we can fill in this larger table very directly. If A and B are 0, that's this block up here, F should just be whatever A0 is. 0, 1, 0, 0. That should be a 1. 0, 1, 0, 1. If A and B are 0, 1, that's this block down here, F should just be whatever A1 is. 0, 0, 1, 1. If A and B are 1, 0, which is this block, F should be a 0. And if A and B are 1, 1, which is this block down here, F should be a 1. So there's your truth table of F as a function of 4 input variables. All right, and like I said, this is something that we call compression. Because this is a big truth table of 4 variables. This is an equivalent truth table, but it's smaller. It's only 4 rows instead of 16, so we've compressed it. But as the cost of that compression, we've changed it so that the output is not always just a simple 1 or a 0. It could be a variable. Well, we can always compress truth tables. Okay, let me give you an example of compression. Another example. All right, 3 variables, f of a comma b comma c, 8 rows in our truth table. We can say, for example, compress this around C, which means let's take C and move it into the output column. So now we're going to have a function of 2 variables, A and B. Okay, so what's the first row here? A is 0 and B is 0. That's these 2 rows. F could be a 0 or a 1. We can't write a 0 because sometimes it's a 1. We can't write a 1 because sometimes it's a 0. So how can we represent the correct value of F in the case where A and B are both 0? Well, guess what? If C is 0, F is 0, and if C is 1, F is 1. Apparently, in this case, F is just equal to C. Next row, A is 0, B is 1. That's these 2 rows in our original table, and in both rows, F is a 0. So here we can just say, you know, if A is 0 and B is 1, F is a 0. Our third block, A is a 1 and B is a 0. Well, here again, sometimes f is 1, sometimes f is 0, so we can't write a 1 or a 0 here. That's not going to be correct. But what can we write? We can't write c, because if c is a 0, f is actually 1. And if c is a 1, f is actually a 0. So it's going to be the opposite of just writing c. So hey, how about this? Yeah, somebody got it, not c. Right? So we can't do a don't care, because we do care. We actually want it to be a 1 in this case and a 0 in that case. But if we write it as not c, right, then in this row where c is a 0, this is saying f should be a 1, which is correct. And if our input is 1, 0, 1, this is saying the output should be 1 complement, which is 0, which is also correct. And then our last case, a is 1, b is 1. That's this block, and this one's easier because f is always 1. Right? So that's a compressed version of this original truth table, and we say we compressed it around c. All right. So question 8 is doing the reverse. They're giving you basically the compressed version and asking you to make the uncompressed version. So for a equals 0, b equals 1, then f equals... yeah, f would be equal to not b, because b is 1, so not b is 0. So that's one way to think of it. Yeah, for a is 0 and b is 1, f is not b. But that's not a generally applicable simplification. That just works out because b happened to be 1. But that would be correct. We can keep going. I'm not going to, but I'll just let you know that you could keep going. Okay, you can say compress around b. And make this a function of one variable. Well, if a is 0, what should f be equal to? It's either supposed to be equal to c or 0. Okay, if b is 0, then it should just be equal to c. And if b is 1, it should be equal to 0. And if a is 1, then if b is 0, it should be equal to c bar. And if b is 1, it should be equal to 1. So we can actually write f as a function of just one variable a, but the values for the two values of a contain b and c. If we compress around a one more time, we end up with a function of no variables, but that function will be exactly the sum of products representation of this truth table. So don't worry about that. We can branch off into deep theory land, but this is the basic idea, just compressing around a variable. Okay. All right, other questions around that? All right, the fuse map questions, we talked about fuse maps already. Hopefully that's making sense. So for question 10, right, you're building a circuit with 8 inputs and 1 output. So 8 inputs means your AND plane is going to have 8 of these lines instead of 4. So I0, I1, I2, I3, I4, 5, 6, and 7. So you're going to have 8 of these, right, running vertically with an inverter coming off of each. And this is just a shorthand way of showing an inverter. So A is the input, this is A, and this is the complement of A. And there's a shorthand here, and you can only use this in fuse maps, okay? Remember when we drew this, we had this idea of an input going through an inverter, and an input going through an inverter, and so on. And then we had an AND gate over here, and we might have connected up the inputs of that to some of these inputs. And here might have been another AND gate connected to some of these inputs. And then we had an OR gate, and we might have picked some of those to OR together, and then here was our output F, right? So drawing this, right, this is a correct schematic. This is actually a legitimate schematic. This is not, right? You can't have one wire going into an AND gate connected to a bunch of different outputs. You're shorting this output with that output and that output. This is not something you could build, okay? Our AND gates need to have multiple inputs. Our OR gates need to have multiple inputs. Here we've got the output of all these OR gates connected together to one wire. So this is not a schematic, okay? This is a fuse map, which is using a shorthand representation of this. Because drawing a bunch of lines from an AND gate to cross over here is confusing and hard to follow. So we use the shorthand notation. We show an AND gate with a single wire coming off, and we just show our connection points to each of these output signals. But the understanding is that in this case there's 4 inputs going into this AND gate. One comes from here, the second comes from here, the third from here, and the fourth from there. Okay, it's a convenient shorthand notation. Similarly with the OR gates, the input to this OR gate is coming from 1, 2, 3, 4, 5, 6 different outputs. And we have at least 6 inputs going into this OR gate. One from here, 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 and there. Right? And then the output's generated here. So this is a shorthand notation, and you're encouraged to use this for fuse map questions, but don't start drawing schematics that look like this, okay? Because if somebody were to actually build this, your circuit would short out, right? You can't connect inputs to a single wire like this. But it's a shorthand, so this is saying, you know, take these 4 inputs, AND them together, and then OR that, you know, with this, 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 and this, and call that result C0. So you're going to build a circuit that has 8 inputs, okay, 16 lines running like this, and a single output, which should be a 1 when the output is unlocking, right? So you're going to have 1 OR gate, and there's 9 combinations that should cause the circuit to unlock, right? This is one of them, this is another 4, this is another 4. So you're going to have a total of 9 AND gates, each one corresponding to one of these bit patterns. And then those 9 AND gate outputs you're going to get ORed together through an OR gate. The output of that's going to be your unlock signal. Okay, so you're making the fuse map for that. Just label your inputs and label your output and fill in the correct crossings. And then 11, you do the same thing, but it's with a prom, so it's only the AND plane that's fixed. The OR plane is programmable. And with a prom, basically you have, you know, so to implement this fuse map from the prior question, right, you needed certain AND terms, right? Well, 4 inputs, we could have a lot of AND terms, right? We might not need to use all of those. So with a prom, the AND plane is fixed, and for every possible combination of our inputs, there's a configuration in this AND plane that generates the corresponding minterm. So for inputs, we have 16 AND gates generating minterms 0 through 15. And our OR plane is really just choosing which minterms we want to sum together. So what's the Boolean expression for this fuse map for F3? It's just M11 plus M12. Why? Because those are the 2 minterms that I'm summing together. So an 8-input circuit, you would theoretically have 256 minterms, M0 through M255. And it warns you here not to draw all of them. Okay, if you're not using minterm 11, don't draw minterm 11. Otherwise, you're going to have, 256 lines here. It's a huge sheet of paper. So just list the min terms that are required and OR them together to get your unlock signal. All right, sound good? So let's talk a little more about Muxers, DeMuxers, decoders, encoders. And this will take us into aspects of Lab 4. Why is the Boolean expression only M11 and M12? Which Boolean expression? For F3? So if you look at F3, the only input combinations that are supposed to generate a 1 are 1011 and 1100, which correspond to min terms 11 and 12. Yeah, in the last example. So F3 is supposed to be 0 every time except when your inputs correspond to min terms 11 and 12, which are these two entries here. So this output of this AND gate will be true when your input is a 1 and a 0 and a 1 and a 0. That's that looks like a typo to me. Oh, sorry, 1011. That's right. Okay, so if this is a 1, that's a 0, and these two are 1s, then this output will be 1, and that's one of the inputs to your OR gate. Okay, cool, you got it. All right, so let's talk about Muxes and DeMuxes and encoders and decoders. So remember our basic setup, right? A mux was something that took multiple inputs and turned it into fewer inputs. So 2 inputs, we can choose one to generate an output from. A 4-to-1 would have 4 inputs, and we can choose which one to send to the output. And you have a series of select bits, and depending on how many inputs you have to choose from, you might have, 1, 2, or more select bits. So for 4 inputs, we need to choose one of 4 things, we need 2 select bits. Okay, and so this is like, the demux from the earlier homework question. Depending on the value of these, your output comes from one of those 4 inputs. Okay, the muxer would basically choose one of 4 outputs. And it would send this input to one of those 4 outputs. And the question is, what should the other outputs be? So let's call these Y0, Y1, Y2, Y3. All right, I don't have bubbles here, so when I say I assert an output, I'm implying I want the output to be 1. Okay. So 1 means, we're doing something to the output. 0 means we're not. So here's what that means for a demultiplexer. So let's say S0 and S1 are both 0. So we're going to take our input, we're going to send it to Y0. So if the input's 0, this will be 0. If it's 1, it'll be 1. If our input is 0, 1, then we're going to take the input and send it to Y1. So if the input is 0, Y1 is 1. If it's 1, if it's 0, it's 0. If it's 1, it's a 1. If our input is 1, 0, Y2 matches the input. And if our select is 1, 1, then Y3 matches the input. Okay, what's not specified here is what is the input in all of these other cases. So what are we going to use? Well, since we don't have bubbles here, right, we're going to make all of these 0. And so one way of looking at this is that exactly one output is going to be 1 if the input is 1. Okay? If the input is 0, it doesn't matter what you do. Anytime the input is 0, all of your outputs are 0. But if the input is 1, then exactly one of your outputs is 1 based on what your select lines are. So there's two ways to look at this. One, it's a way to route your input to one of 4 outputs. But you can also look at it as if our input is 1, we can use this circuit to assert one of our 4 outputs. Whereas if our input is 0, we don't assert any of our outputs. So sometimes you see a 2 to 4 multiplexer written with this input labeled something like EN for enable. And so we could take this truth table and we could write it more simply as follows. Something like this. If the enable input is 1, then one output is active. If it's 0, 0 on the select, Y0 is active, 0, 1, Y1, and so on. If the enable input is 0, all of the Yi are equal to 0. So different ways of thinking about this, right? At the lowest level, it's all truth tables. 1s and 0s in the inputs, 1s and 0s in the outputs. But it's a great deal of power and convenience to be able to think of these differently sometimes, right? Based on what the behavior is intended for these circuits. So here we can think of it as asserting exactly one output when the chip is enabled and deasserting all the outputs when the chip is not enabled. And that goes along with some of the terminology you'll see inside some of the data sheets. So if we look at component specifications, and let's look at so this is a 3 to 8 decoder or DMUX, and there's our 3 select lines A, B, and C, and here's our 8 outputs Y0 through Y6 with Y7 down here. And then there's a series of enable inputs. Okay? And the enable inputs basically say whether an output's going to be asserted or not. And there's bubbles on all of the outputs. So here asserted means 0 and deasserted means 1. And if you go down to the truth table for this, you can see the truth table output for most of this, right? Depending on the values of A, B, and C, exactly one output is asserted low, and all the other outputs are asserted high. Okay, so if your input is 1, 1, 1 or high, 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 it's Y7 that's asserted low. If it's 0, 0, 1, then it's output 1 that's asserted low. And this is true for these bottom 8 rows of the truth table. The top 2 rows show you that nothing is asserted, right? And so this happens, this chip works the way it's supposed to when this thing called G1 is high and this thing called G2 star is low. Okay, and it tells you G2 star is G2A or G2B. So we need this OR to be low, which means G2A is 0, G2B is 0, and G1 is 1. Well, if you go back to this picture of the chip, this enable line G1 goes into the chip without a bubble. So to enable it, G1 has to be a 1. But G2B and G2A have bubbles on the end, which says to be enabled, right, these both need to be 0 so that when they get inverted, you have a 1 going in. So this has to be 0, 0, and 1 for the chip to do anything interesting. Okay, so once you know how to read these pictures, right, you can interpret that from the picture itself, but you can also come down to the truth table and see that explicitly. Although, you know, there is no G2 pin, so there's an asterisk and it tells you G2 means the OR of those 2 pins. So all these data sheets, right, they come in different varieties. Different manufacturers have different ways of writing these, and sometimes, you know, you'll see something with a bubble on the input and a bubble on the output and a few bubbles in between, and you just kind of have to take it as you know, believe that this is the accurate data sheet and work through it and see what it says. Okay, it's kind of like question 8 in the homework. It may not look like something you've seen before, but if you believe that this is accurate, right, just apply your understanding, and it should lead you to being able to work with the device. All right, so those are Muxers and DeMuxers, but there's particular Muxers and DeMuxers that we find useful beyond just routing signals or compressing truth tables. So one you're going to find really, really useful in lab 4 is a 74HC47. Okay, and this is a decoder. So it kind of works like a DeMuxer. It takes a few pins and it drives more pins. So let's pull up a 7447. So this is called a BCD to 7-segment decoder. And I'll show you what's inside. It's all of this stuff. So if you don't know how to use this chip, you're going to have to build this yourself in Tinkercad. Don't do that, okay? It's a fun exercise, but it's not fun as part of a lab. But this is all the circuitry that's inside. Okay, this is what you're spared from if you know how to use this chip. So here's a truth table for the chip. Okay, and you know, here's a truth table for a 49. This is for a 48. We're using a 7447. So here's the truth table. And it's got a lot of inputs. It's got an LT bar, an RBI bar, a DCBA. Okay, here's another notational thing. When you see an input with a bar on top, it probably means active low. It probably means that in the picture there's a little circle next to it, but maybe not. Okay, if we look at the diagram for this, there's an LT bar, there's no bubble. Okay, but it means active low. If we come down here, LT bar, well, there's a funny little thing here, which we can take to be an inverter. All right, so go to the truth table. Truth table is always the definitive source, okay? So LT bar for most of this truth table wants to be high. Okay, it does special things if it's low. If LT bar is low, guess what? None of these other inputs matter. All of your outputs are asserted. So usually we want this LT bar input to be high. And RBI we usually want to be low. If it's high, then something else happens over here. So we're going to usually leave RBI pulled low. And then 4 inputs A, B, C, D, and we have 7 outputs A through G lowercase, and they turn on and off depending on what the inputs are. Okay, just some random looking pattern here. All right, so what is this chip doing? It's working with what's called a 7-segment display. Okay, so let me bring up Tinkercad. Oh, let me not do this because I didn't prep it. So 7-segment display. It's basically 7 light-emitting diodes laid out in horizontal or vertical bar. And there's a series of pins, right? This sits in something that looks like a chip, and there's a series of pins, A through G, and there's other connections that you have to do something with. But the basic idea is if you put voltage through pin A, one of these segments lights up. If you put voltage through pin B, another segment lights up. And if you look at this picture, here's what the segments are labeled. So A on top, B, C, D, E, F, and then G in the middle. So if I choose to light segments A, B, G, E, and D, my display will look like the number 2. Well, guess what? If I put the number 2, 0, 0, 1, 0 into my 7-segment display, which segments are turned on? A, B, D, and E, and G. Right? Which is exactly what we wanted to make this display look like a 2. So by turning on and off different segments, we can make this thing display what looks like a number. If we want a 5, we can turn on these segments. If we want a 6, we can turn on these segments. If we want an 8, we turn on all the segments. If we want a 1, we just turn on those 2. So we could make a truth table that says, you know, if my input is 1000, that's binary 8, we want all of our segments to turn on. Well, that's what this truth table is. Here's input 1000, that's the number 8. All of your segments are on. Here's input 0001, that's the number 1. You only have 2 segments on, B and C. That's these 2 segments here on the right. So this chip will take 4 inputs and turn on the proper segments to make the 7-segment display look like any of these 16 symbols. And 0 through 9 look like 0 through 9, and 10 through 15 look like the wristwatch Alien War, or Predator War, for his countdown device. So this is a really useful chip, okay? Because Lab 4, you're going to build a circuit that does addition. And you want to display your result not in binary, but on a 7-segment display with a nice digit. So you're going to build a 2-bit adder, and then you're going to take the output of that, run it through this 7447 chip, take the output of that chip, connect it to a 7-segment display, and then use that to see what your numeric answer is. All right, so let's take a 5-minute break. And we will come back and let's take a closer look at Lab 4 and talk about adders. All right.